Let us continue the solution for this ninth series of AEC and ME. So in the previous video we were discussing about the Schmitt trigger. So we have actually done these two problems. So we found the value of R1, R2 and V reference voltage. So let us find it out for these two. So okay, this is the third problem where VTH is 4 volt and VTL is 1 volt. So both are on the positive side. So as we did in the previous video, so we are taking the difference of VTH and VTL, which comes out to be 3 volts, which will be equal to 2 times Vsat R2 by R1 plus R2. So when I'm referring to this equation, so you should always remember this circuit diagram. So this is the inverting Schmitt trigger circuit diagram having R1, R2 and V reference, and of course the input is applied to the inverting terminal. So for that circuit these equations are valid. So upon equating this, so we will get a relationship between R1 and R2 as this by adding VTH and VTL and substituting R1 in terms of 7 by 3 R2 and simplifying, we got V reference as 3.57 volts. So the value of R2, if you assume it to be 10 kilo ohm, then R1 happens to be 2.33 times 10k, which is 23.33 kilo ohms. Fine. And then we actually did it for the another value, which is VTH is equal to -2 and VTL is equal to -3. In all the cases, if you can notice, VTH is always more than VTL. You can see it is 3. Okay, one is positive, negative. Here this is positive, negative. Here it is positive. Again this is positive, but here both are negative. In whichever combination you see, VTH is always more than VTL. So that's the requirement, or that's the property of this inverting Schmitt trigger. VTH can never be lesser than VTL. So keeping that in view, we are actually finding what is R1, R2 for this VTH, VTL. Of course, we are assuming that plus or minus Vsat as plus or minus 5 volt. Keeping those things, so we got the values of reference voltage as -2.77, and this is 10k and 90k as R1, R2 values. And it was also asked to write the transfer characteristics for these two. So let us try to write the transfer characteristics for these two. So transfer characteristics is nothing but output versus input. Now this is your minus V0, and this is V0 here, this is V in, and this is minus V in. This is 0. Now let us identify the threshold voltages, which is for this case it is 4 volt and 1 volt. This is not exactly the scale, it's fine. So now let us assume that this is plus 5 volts and this is somewhere here. Okay, let me write it as, this is somewhere here, minus 5 volts, minus 5. Now so if the input voltage is less than 4 volt, output will be plus Vsat, and if the input goes above 4 volt, the output goes to minus Vsat. This is how the transition, and it goes till here, then it will come back in the negative half cycle. Sorry, since your VTL is 1 volt, so if the input voltage goes less than 1 volt itself, the output will have a transition from minus to plus. So this is how it is going. It goes here, and then even if the input voltage goes negative, so output will be at minus Vsat. This is how it is going here, and if it is again increases, it goes this way. So this is the traversal of this is 4 volt, this is 1 volt, and here it is plus 5 volt. If the input is lesser than 1 volt, it will be plus 5. If it is more than 4 volt, it will be minus 5 volts. If it is in between, assume that input is 2 volt. If the previous output is VCC, it remains at VCC, that is plus 5 volts. If the previous output is minus 5, it remains at minus 5. So this is the transfer characteristics. Transfer characteristics of negative Schmitt trigger or inverting Schmitt trigger. Inverting Schmitt trigger. Let us do it for this. This is having, both are negative now. So now let me write this axis. This is V in positive, this is minus V in, this is V naught, minus V naught. So now I have the threshold voltages as minus 2 and minus 3. Let this be minus 2, let this be minus 3. That goes this way. If the input voltage is more than minus 2, so more than minus 2 is towards positive side, the output will be minus V sat. This is how it goes. And of course, if this is your maximum of input voltage, then it again come back here. The input goes below VTL, output goes to high state. You can see this is the traversal. It again goes. This is how this is going down, and this will again go back. This is going like this, and again goes this way. This is the input peak. You can take it as 5 volt, and this as minus 5 volt. And output is of course plus V side, which is the dotted line, plus 5 volt. This is minus 5 volts. Okay, this is again the transfer characteristics of this VTH VTL, and the circuit is this. This is the circuit. So now let us see the other part. Now you are asked to find what is VTH VTL given the values of R1, R2, V reference. Of course, this is straightforward, which you can easily find, and of course we are assuming still plus and minus V set as what? Plus 5 and minus 5. So if I just go back, it's a simple one, so I'll just do only one, so which you can easily repeat. So what is this VTH VTL? So let me write it here. So I have R1 is equal to 2 kilo ohm and R2 is equal to 1 kilo ohm. V reference is 0.8 volt, and of course plus or minus V sat is plus or minus 5 volt. Maybe I'll do it for one more, which is R1 is equal to 4 kilo ohm, R2 is equal to 2 kilo ohm, but V reference is 0. V reference is 0 volt. Again plus or minus V sat is plus or minus 5 volts, plus or minus 5 volt. So equations we know already. VTH is equal to V sat into R2 by R1 plus R2. Okay, let us always keep in mind. So whenever you write the answer for any of the circuit, any of the specification, first and foremost thing that we need to write the circuit diagram. This is minus plus. I have this. This will go here. This will go here. This is V reference. This is R1. This is R2. This is my input voltage. So this is V naught. So this is the circuit, and this is the equation V sat R2 by R1 plus R2 plus of V reference R1 by R1 plus R2, and what is VTL? VTL is exactly minus V sat into R2 by R1 plus R2 plus of V reference into R1 by R1 plus R2. Let us try to find what is VTH VTL for these two. So I have, it is now for the first case, it is 5 into 2 by 3 plus of maybe 0.8 into it is okay, sorry, this is 1, this is actually 1 by 3, because this is R2 by R1 plus R2, and this is actually 2 by 3. So this is now, it's actually R1 by R1 plus R2. So R1 by R1 plus R2 is 3K, because K I'm just taking it out. So now this is 2.22. So this is now VTH is 2.2. let me just complete the, because I already have the VTH equation, so let me replace this by, it is now 2 by 6. 2 by 6 happens to be same, 1 by 3 only. Next it is, V reference is actually 0. You make it as 0.0, and it's again now, it's now 4 by 6. 4 by 6. So what is the voltage? So voltage here is 1.66. This will be naturally minus 1.66. So this is 1.66 minus 1. Because there is no V reference here. But for this, let me find out. So it is now minus 5 into, because VTL is minus 5 into R2 is 1 by 3 plus of V reference is 0.8 into 1, okay, 2 by 3. So I have this as minus 1.13 volt. This is minus 1.13 volt. So here you can see when the reference voltage is 0, VTH, VTL are having same magnitude. Only thing is that there is a sign change. But when when V reference is other than 0, so VTH, VTL will be totally different, and their magnitude will also be different. Okay, that's it, fine. So let us go back and see what is that next we have. Okay, you can write the transfer characteristic for this, so that's not a big issue. Okay, that's it for this Schmitt trigger. Let us see what we have in. Okay, let me just look for AEC and 11. So 10 is of so 10 is, I think it's of, okay, I'll come back to, so I'll come back to this, okay, slew rate one maybe a bit later, so that needs some information about the slew rate. So let me just, okay, tackle this. So what you have is a square wave generator with the timing resistor as 10K, and then you have 0.1 microfarad as CT, and of course you have R1, R2 as 2.2K and 2.2K. So let us find what is the frequency and the waveform. So let us assume that for the time being slew rate is infinity. So let me write the circuit now here. So this is circuit I have. This is my capacitor. Assuming the opamp is ideal, so we are just trying to write the output waveform for this square wave. This is 2.2 kilo ohm. This is also 2.2 kilo ohm, which is R1, R2. I will ground this. This is my timing capacitor, which is 0.1 microfarad. This is timing resistor RT. Okay, RT is first time it is 10 kilo ohm, then it is 100 ohm. So let us do it for both of them. Fine. Okay, this is the circuit what I have. So this is actually a square wave generator. Square wave generator. Square wave generator. So we know that, of course, this is again since the feedback is positive. Of course, this is not negative feedback. For of course, this is actually a feedback given to the capacitor so that it can charge to the available output voltage V out. So again, since it is positive feedback, V out is either plus or minus V sat. So you will not get voltage anything other than plus or minus V sat. So now this is the waveform we are looking at. So we have output voltage plus V sat, it will go to minus V sat, and then it will again go to plus V sat. This will have a transition like this. Okay, this is plus V sat, this is minus V sat. and the capacitor charging discharging happens this way. The capacitor charges from minus beta V sat to plus beta V sat, and this is again from plus to minus, goes this way. This is exponential charging discharging. Suppose if I mark this point, it is plus beta times V sat, this is minus beta times V sat. So this beta is nothing but R2 by R1 plus R2 with this orientation of the resistance. If this is R1 R2, then beta is R1 plus R2 by R1 plus R2. Now of course we know the expression for the on time is same as the expression for off time, because we have the same charging and discharging path for this capacitor, which will be given by RT CT natural log of 1 plus beta by 1 minus beta. So since the value of R1 R2 is given as 2.2k 2.2k, suppose if you substitute that, this will be 2.2k by 4.4k, which happens to be 0.5. So beta is 0.5. If you take the value of RT as 10 kilo ohm, so then T on is equal to T off is equal to 10k multiplied by 0.1 microfarad ln of 1.5 by 0.5. Because we have beta as 0.5, 1.5 by 0.5, you can actually find out what will be this time. It is 10 exponential minus 6 into 10 exponential 3 into 0.1 exponential minus 6 into ln of 3. This is 1.09 millisecond. This is the T on is equal to T off. Then what is frequency? Frequency is 1 over T, which is nothing but 1 over T on plus T off. So I'll simply make it into 2 4.5. So it is 455.1 hertz. So this is the frequency of the signal, and the output voltage is 5 volt. This is minus 5 volt. This will go up to 2.5 volt. This is up to minus 2.5 volts, because it is beta is 0.5 into 5 and minus 0.5 into, or 0.5 into minus 5, which is minus 2.5. So this is the frequency. So duty cycle, we know that it is T on by T on plus T off, because T on T off is equal to or both are same, then this has to be a 50% duty cycle, 50% duty cycle. So this is assuming slew rate is infinite volt per microsecond. So it doesn't take any time to go from plus V sat to minus V sat, or from minus V sat to plus V sat. This is minus 5 volt. Okay, let us repeat the same thing with, let me just repeat this with 100 ohm. If it is 100 ohm, so what will happen to this? The frequency will increase by, this is you are reducing it by how much times? So maybe 100 times. So 100 into 100 was 10k. You are reducing it by 100 times. So this also will reduce by 100 times. So it is 1.09 exponential minus 3 divided by 100, which happens to be 10.9 microsecond. So then this is into 2, 1 over that will be 45 point. So you have 45.87 kilohertz. So this will be the frequency of oscillation if the resistance is reduced from 10k to 100k. It actually increases by 100 times. So it is 455 into 100 happens to be 45.5 kilohertz. Okay, that's what is 45.87 kilohertz. So this is how you can find out the frequency and the duty cycle of this. Again, I'll come back to slew rate in another video. So for the time being, you can just hang on to this. Let us try to find out what is the again duty cycle and frequency of this circuit. So So this is slightly a different circuit. You have two different paths for the this capacitor to charge during while charging and discharging is totally a different resistor. So naturally the time constants will change. So once time constant changes, the on-off time will also change. Let me rewrite the circuit in my book. I'm just doing the same. It is minus, plus. So there is a feedback through R1, R2. So R1 is 10K, R2 is 1K. This is R1, R2. And I have a capacitor of 10 microfarad. This is 10 micro. And I have a resistor R2 through this diode. Okay, let me just connect it this way. And that RT2, and there is one more RT which is in the opposite direction diode. So this is D. Let me say it as RT2. This is CT. Okay, this is my V0. Okay, let me just go back. Okay, RT1, RT1, RT2 are assumed to be. RT1 is 4.7 kilo ohm and RT2 is 1 kilo ohm. 1 kilo ohm. Okay, if these two are the timing resistors, let us find out what is. Okay, let me find out. So this is specifications. Again, now we know that the capacitor will charge to plus Vsat. When it is plus Vsat, this diode is on. So shall I say this as D charge, this as D discharge. Now this T1 is associated. Okay, let me write which is T1. Oh, which is T1? T1, let me find out. Written. Okay, this is T1. This is RT1. This is RT2. Meaning this is RT1. So while charging, it will pass through this. While discharging, it will go through this. So this is what. So shall I say RT1 is RT charge. This is RT discharge. So now you have the charging time is more than discharging time. Naturally, when you have the output voltage like this, so now since charging time is more, because you have the same capacitor and RT1 is more than RT2 by almost 4.7 times, naturally this is because it takes longer time to charge. So this is so like this, and the discharge time is very quick. So now maybe only this much. So this is actually going 5 times, 4.7 times, and this is hardly. Suppose if you say this is 1 time. So if you can see now, this is actually plus Vsat minus Vsat. What is beta value? Beta value is not 0.5. Beta is actually 1K by 11K, because it is R2 by R1 plus R2. It is R2 by R1 plus R2. This is actually 1 by KK will go off. It is 1 by 11. So 1 by 11 is hardly 0.9. So it is 1 by 11. So it is 0.0909 into 5 is okay. Now let me find out what is the voltage. Can you see it is now plus or minus beta Vsat is equal to plus or minus 0.454 volt, meaning this is, suppose if you consider this as minus beta Vsat, it's actually going like this. This is your capacitor voltage, charging discharging. Because beta is so small, it goes like this. Can you see it takes longer time to charge, whereas the discharging is faster, because you are associated with RT charging. This is okay, proportional to, this is proportional to RT discharge, because discharge resistance is very less, it discharges quickly. This resistance is more, it takes longer time to charge. So this is T on, T off. Neglecting the diode on resistance, treating it as ideal. What is T on expression now? It is RT charge into CT ln of 1 plus beta by 1 minus beta. So coming to expression, it not 4.7 K into 10 micro? L enough? L enough? Okay, now it is 1 plus 1 by 11 to 1 minus 1 by 11. So now this is so how much is this? So this is 4.7 into 10 milli L enough. So is it not 12 by 10, which is 1.2? So it is now 4.7 exponential of 3 into 10 exponential minus 6 into L enough 1.2, because this is now 11 plus 1 is 12, 11 minus 1 is 10, L enough 1.2. So this is coming out to be 8.56 millisecond. So this is my T on. So what is T off? T off is same expression, but only thing is that this resistance will change. So T off is equal to RT discharge CT ln of, of course this ln remains the same, it is 12 by 10, ln of 1.2. So what is this now? It's actually 4.7 times lesser. Is it now 1 exponential 3 into 10 exponential minus 6? Oh, this is 10 exponential minus 6 into ln of 1.2. Can you see it is 1.823 millisecond. This is T off. Actually, if you do that, 8.56 by 4.7 would be 1.86. So 1.8. So this is what is T off. So now what is the frequency? Frequency is 1 over T on plus T off, which is equal to, so it is 1.823 plus 8.56. Okay, it's actually into, it is 8.56 exponential minus 3 into exponential minus 3. Oh, sorry. So let me find out what is this. 8.56 exponential minus 3 plus 1.823 exponential minus 3. Add this. 1 over that is 96.31 hertz. Duty cycle coming out to be T on by T, that is 8.56 divided by 8.56 plus 1.823. So it is 82.44%. Because this on time is more, off time is less, you have a duty cycle more than 50%, it is 82.44%. Okay, this way we can able to find what is the square wave generated using this. So this is plus 5 minus 5, and of course if you want to find this voltage, okay, this is actually plus 0.45, this is minus 0.45, this is plus 5, this is minus 5. Okay, this way we can able to find we can able to get the waveform for the square wave generator for duty cycle other than 50%, and this is for 50% duty cycle. You can see here it is duty cycle comes out to be 50%.